So this is the lesson on particle motion. We've did the lesson for 2 class blocks. Some classes have gotten through more of it than the others, so I just wanted to have the whole lesson someplace for you guys to refer back to. So for the warm-up, we first just used the first and second derivative test to find the x values of the maximums and mins. So using your first derivative, ooh, that is large. And, you can fast forward, rewind, pause, see if you could do the questions on your own during this, whatever you want. Also, this lesson is a great reference to Beyonce's one of her greatest hits, Irreplaceable, or better known as To the Left, Everything You Own in a Box to the Left. So if you've never heard it, YouTube it right after this. All right, so first derivative is going to be 15x to the fourth minus 15x squared. We're going to set that equal to 0. I'm going to factor out the 15x squared. We get x squared minus 1, 15x squared, x plus 1, x minus 1. And now I'm going to make my little factor chart. My critical values are going to be 0, x equals 0, x equals negative 1, and x equals positive 1. Okay, so every one of my factors, I have 1, 2, got a multiplicity of 2 there, so I got 4 factors total. All 4 of them will be negative, any number less than negative 1. So if I have an even number of negative factors, that's going to be a positive. After I do negative 1, that would be this factor here would no longer be negative, so now I have 3. Odd number of negative factors is going to be negative. Then I go by 0, and both of these factors are gone. So now I'm down to 1, so that would also be negative. And then take out that one. Now I'm down to 0 negative factors, which would be a positive number. So that tells me that I have a relative max right here and a relative min right here. And this asks us to find, it just asks us to find the x value, so I don't have to worry about subbing back in to get the y values. So relative max at x equals negative 1 and relative min at x equals 1. Didn't say to justify, but if it did, I would say relative max at x equals negative 1 because h prime of x changes signs from positive to negative. And for the relative min, I would say h prime of x changes signs from negative to positive, and I would write the whole thing out. Okay. And then we got our second derivative test. So we're doing the same thing, only using our second derivative here. So h double prime x is 60x squared, 60x cubed minus 30x. And now what we do is we take our critical values, which we found from our first derivative, and we're just going to sub it in, because if our first derivative equals 0, then it probably is going to be a max or min, except in this case for 0, it'll fail. And when that happens, you would need to refer back to your first derivative test, which we already have. We see 0 is nothing because it's negative and then negative again. So it does have that horizontal tangent line there. It's just still decreasing. H double prime of 1, we sub in 1. Okay, so we see that that is 30, which is a positive number. It's greater than 0. So that means it would be concave up, like a cup. So if it's positive, or think happy face, that tells you that there's going to be a relative min there. and then h double prime of -1, we get 60 times -1 cubed minus 30 times -1, and that's -30, which is less than 0. It's a negative number, so that's going to be concave down like a frown or sad face. Negative think sad, so that's going to be a max right there. So we get the same values here. We get relative min at x equals 1, and we got a relative max at x equals -1. So same thing, most of the time I would say in a problem like this, I probably just use the first derivative test, but you can also use your second derivative test, especially if you have a tricky derivative where you only, where it would be more convenient to use that. All right, so when you're discussing motion, we have 3 closely related concepts. So the first one's going to be position. And a lot of times they refer to that as x of t. So that determines where the particle is located on the x-axis at a given time t. Okay, next one would be velocity, which is going to be your first derivative of position, so x prime of t. Sometimes they'll refer to it as v of t, v for velocity. Rocket science, right? Literally calculus. All right, determines how fast the position is changing at a time t, as well as the direction. Sorry about my sloppy handwriting on the iPad. And 3 is acceleration. So that's going to be your second derivative of position. First derivative of velocity, and they may refer to it as a of t. We want to be careful. We want to refer to it as however the problem refers to it. And that determines how fast the velocity is changing that says changing at a time t, and the sign indicates if it's increasing or decreasing. And it meaning velocity, if the velocity is increasing or decreasing. All right, initially means when t equals 0. At the origin means when the position, x of t, equals 0. At rest means v of t, velocity equals 0. If the velocity of the particle is positive, then the particle is moving right or up. If the velocity of the particle is negative, then the particle is moving to the left or down. To find average velocity over time, divide the change in position by the change in time. Instantaneous velocity is the velocity at a single moment or instant in time. If the acceleration of the particle is positive, then the velocity is increasing. If the acceleration of the particle is negative, then the velocity is decreasing. And in order for the particle to change direction, the velocity must change signs. All right, so the first question here asks us to determine the total distance traveled over the time interval. So we can find the sum of the absolute values of the differences in the position between all resting points. So think about testing your endpoints and your critical values. just like when we were getting absolute max or mins. And then we're going to see how far it's traveled between those. So if I take my first derivative here, that's going to give me my velocity. So that's going to be t squared minus 2t minus 3. Set this equal to 0. T minus 3, t plus 1. So the velocity equals 0 at 3 seconds and at -1 second. Now our domain just goes from 0 to 6, so we're not talking negative time here. So I'm going to reject that -1, not in the interval. Then I'm going to make a little chart. So here's time. Here's my position. So remember, you're going back to your original function to get these values. When I plug in 0, I get 4. When I plug in 3, here's where my particle is changing position because it equals 0, or it's at rest. Actually, we'd have to make a sign chart to figure out if it was changing position. And then at 6, it is at 22. All right, so going from 4, so picture the particle. Here we are at 0 seconds. He's moving, I don't know why the particle is a he, but he's moving 4 units this way. So we've gone 4. Now we're moving this way, and we're at -5 right here. Actually, hold up. Let me erase that for a second. We're at t equals 0, we're starting at 4. He's not moving 4. So we're starting at 4, position 4. Then we're moving backwards. We're at position 5. So we've moved 9, right? 9 units to the left. And then we're going all the way at 6, we're at 22, so we'll say like somewhere out here. So that's 27 units, going from -5 to 22. So the total distance this particle has traveled, you're just going to add up the 9 and the 27. And that will be 36 units. All right, another thing that a lot of you guys probably know from physics already, but the particle's speeding up when the velocity and acceleration have the same sign. So either they're both positive or both negative. All right, so let's go through this first example. Particle is speeding up. I've been using purple. Let's change that to blue. Particle speeding up. Oh, we already did that. The position s in meters of a particle at time t in seconds is given by the function s of t equals t cubed minus 12t squared plus 36t. All right, velocity at time t is going to be the first derivative of this position that they gave us. So I'm going to say s prime of t. And it's 3t squared minus 24t plus 36. So whatever this original function is, I just always am going to refer back to it. I'm not going to call it v of t, I'm going to just call it s prime of t because I'm referring to that function. Velocity at 3 seconds, now we're just plugging in a 3. Into our velocity function, which is s prime. And that's -9. Make sure you have your units. It's meters per second for this one. When the particle is at rest, well, we're looking for when our velocity equals 0. So I'm going to set my velocity equal to 0. Now I'm going to factor. It's going to be 0 equals 3 times t squared minus 8t plus 12 So that's 0 equals 3. We got t minus 6, t minus 2. So that's going to be t equals 6 seconds, and t equals 2 seconds. 2 times when the particle's at rest. When is the particle moving forward? So we're going to make our sign chart for that. So I'm using this right here. And we have our first derivative, which is velocity. And we got 2 and 6. And that's going to be plus, minus, plus for our factors. We got 2, 1, 0 for the negative factors there. And our time's going to start at 0 here, so I'm just going to put an end onto this sign chart. So when is it moving forward? When our velocity is positive. So we're going to write 0 to 2 seconds and 6 to infinity seconds. They did not restrict our domain, so we're going to keep it like that. Total distance traveled from 0 to 8 seconds. So we're going to take those endpoints and the critical values. So we got t and s of t. So our endpoints are going to be 0 and 8. And then we have the 2 and the 6, the critical values from part C. So 2, 6, and then we have 8. Sub in those values, you get 0, 32, 0, 32, nice little pattern there. So each time, absolute value, we're going 32. So that's going to add up to a total of 96 meters. All right, acceleration at 3 seconds. Now we're looking at our acceleration, which would be your second derivative. So we're going to do, what is this called? S double prime of t, and that's going to be 6t minus 24. So at 3 seconds, we're going to do s double prime at 3 seconds. It's going to be 6 times 3 minus 24, which is negative 6 meters per second squared for acceleration. Whether the particle is speeding up or slowing down at 3 seconds. So what we want to look at is the signs of our velocity and our acceleration. So our velocity is s prime at 3 seconds, which we figured out was negative 9 meters per second. We figured that out in part B. And then in part F, we just had figured out that the acceleration at 3 seconds, s double prime of 3, was negative 6 meters per second squared. So what I'm looking at is my signs, and they're both negative. So that's the same sign, which means the particle is speeding up. Both signs are negative, so we got the same sign. So the particle is speeding up. So I'm going to write out an explanation. S prime of 3 and S double prime of t of 3 are both negative. So the particle is speeding up. And notice I referred to our problem. I named this specifically. The function was s. I didn't just say like velocity and acceleration, so that's important to remember to do. All right, so same type of problem, only the algebra gets a little bit tricky in here. First off, when we're finding our velocity, that is going to be the first derivative, right? It's going to be x prime of t. And we need to use a quotient rule for this. Great opportunity to go back and YouTube the quotient rule song, one of my favorites. We got low d high minus high d low. Square the bottom, 1 plus t squared, and away we go. Negative 2t over 1 plus t squared. All right, when is the particle moving to the right or the left? So we got to do a sign chart for that. So I'm going to set my velocity equal to 0 over 1 plus t squared. All right, so this function will equal 0 when our numerator equals 0, so that's going to be t equals 0. Nothing is going to make this equal 0, the denominator, because this number turns out to be squared, so there's no way we can get like a -1 in there. All right, so here we go. 0 is our sign chart. Anything less than 0, this whole function will be positive. Anything greater, it's going to be negative. I'm going to kind of cross out this section right here, the time being less than 0. So I'm going to say moving right would be when your velocity is positive. That's going to be never. And then moving left, I would say from 0 to infinity seconds. Well, I guess, yeah, we're talking seconds. I was going to say what was the time given in. All right, what's the total distance traveled in the first 3 seconds? So again, total distance, you're making a chart. So we got x of t, original function there. Our endpoints are going to be 0 and 3. And we don't have any critical values in between because we only have that critical value of 0, which is also an endpoint. When you plug in 0 into your original function, you get 1. When you plug in 3, you get 1/10. And the difference between 1 and 1/10 is 9/10 units. All right, on what intervals is the acceleration positive or negative? All right, so here's where we have some real fun algebra. So we have to do quotient rule again using our first derivative, which is over here, just to refresh your memory. So we're doing second derivative as our acceleration. And that's going to be low d high minus high d low. That's a little chain rule there. So I got to multiply it by the derivative of that inner function there. And square the bottom, and away we go. All right, so now we have to simplify this. I'm going to write this as -2, 1 plus t squared plus 8t squared, simplifying that whole second term there. 1 plus t squared over 1 plus t squared all to the 4th. So this actually turns out nice because we have a 1 plus t squared in each term in here, so I can kind of simplify that a little. So that's going to be -2, 1 plus t squared to the first power plus 8t squared. That will just cancel out, and then it's going to be over 1 plus t squared to the third power. Then you can just distribute and simplify your numerator. So that's going to be it'll be 6t squared minus 2 over 1 plus t squared cubed. And then we have to make our sign chart. So not a ton of room on this problem, but Set my numerator equal to 0 to see when this whole function is going to equal 0. I get t squared equals 1/3. Take the square root. Don't forget to do plus or minus when you're taking the square root. So plus or minus radical 1/3. This one, again, is the same thing as last time. We're never going to get a 0 in our denominator. So what we're going to do is make our sign chart. This is x double prime, x prime, yeah, double prime. Negative radical 1/3, positive radical third. Think about numbers here, think about like a large number when you're going in the negatives, what that's going to do to your numerator, what it's going to do to your denominator. So if you have a large number for your t, that's going to make your numerator positive, and your denominator is always going to be positive, because even if you have a negative number, when you're squaring it, it's going to be a positive number. So it's going to be positive over positive. That would give you a positive value. Here, I probably would think about what happens with 0 on this one. So if you plug in 0, you're going to have -2 in your numerator. So you're going to have a negative, and again, the denominator is going to be positive. That's going to give you a negative. And then think about a large number. Numerator is going to be positive, denominator is going to be positive. That's going to give you a positive right there. So that tells you that your acceleration is positive. Well, I don't really care about the negative numbers here because we're talking time, so I would probably just think about this part of my graph. So I'm going to just say my acceleration is positive from radical 1/3 to infinity. And then I'm going to say my acceleration is negative from 0 to 1/3, or 0 to radical 1/3. And what are we talking here? Seconds, right? Okay, then let me do a different color. Is the particle speeding up or slowing down at t equals 2? So did we figure out v of 2 already? V of 2, we can look at our little sign chart over here. And that was this one, right? X prime would be velocity. So v of 2 is going to be negative. I don't care what the actual number is. I just need to know if it's negative or positive. A of 2 would be over here on our sign chart. That would be positive. So we have different signs, which means it's slowing down. It doesn't say to justify, but if it did, I would write like a nice justification, like v of 2 is negative and a of 2 is positive, so they have different signs, so the particle's slowing down. All right, so here's some AP questions. What we're looking at is just the original function right here. Particle moves along a straight line. The graph of the particle's position at time t is shown above for 0 to 6 seconds. The graph has horizontal tangents, so they're stating that, so I'll just draw them in. That seems to be important. Horizontal tangents at t equals 1 and t equals 5. So we know that our velocity equals 0 at those. Point of inflection at t equals 2. So here's where the concavity changes in our original function. We can kind of see that it's changing there. For what values is the velocity of the particle increasing? So it's not asking us when our velocity is positive, it's asking us when our velocity is increasing. If the velocity is increasing, that means your acceleration is positive. Your acceleration is positive when your second derivative, which would be x double prime of t, in this case, is greater than 0. Well, when is it greater than 0? That's positive, so it looks like a happy face, which is concave up, like a cup. So we're given the original function, so we're looking at when is it concave up? that value right there from 0 to 2, which is choice A. Okay. Next one. Okay, so this is a calculator question. Unfortunately, I don't have a graphing calculator app on my iPad. So I'll explain as best I can how to put this into the calculator, but the particle move, and this was a calc active question. This would be even to take the derivative, you could, but you're not going to be asked about it on the AB test. Maybe on the BC test, but not on our AB test. All right, so the particle moves along a straight line with the velocity that's given right here. What is the acceleration of the particle t equals 3? So it's a pretty straightforward calculator question. You're going to go to Math 8 on your TI-84, and it's going to say n deriv. And then you're going to type in, it says d dx. And you're going to type in 7 minus 1.01 to the negative. Just use the variable x instead of t. And then it's going to say, it'll have that line, and you're going to say x equals 3. It'll just calculate it for you, and you get 0.055 when you plug that in. So the derivative of velocity is acceleration. That's why you're putting it in like that. Okay, this next one, also a calculator active question, but surprise, you don't need your calculator for it. The table gives selected values of the velocity of the particle along the x-axis at the time t equals 0. The particle is at the origin. Which of the following could be the graph of the position of the particle from 0 to 4 seconds? All right, so I see a critical value right here, our v of t equals 0. And then if this does it say continuous function? Well, all of our graphs are continuous, so I guess we can assume it's continuous. It's going to have to equal 0 somewhere in between there, in between -1 and -2. I'm not sure exactly where. So like if I'm making a velocity sign chart, past 3, it's negative, and then in between 3 and a little, like, I don't know, a little bit more than 0 probably, if this is 0 right here, it's positive, and then over here it's negative again. So if we look at choice C, that kind of has that little negative portion right here, decreasing. Actually, let me do that. It's decreasing a little bit right there. Then it's increasing up until 3. Increasing here up until 3. And then after 3, it's decreasing again. So that's our answer. Okay, now we have some graph questions. So we got the velocity of a particle in feet per second moving along the horizontal line from 0 to 6 seconds. On what open intervals is the particle at rest and justify? Okay, so the particle is going to be at rest when we are crossing that x-axis there. So that's going to be at t equals 1 second and at t equals 4.2 seconds. Justify v of t equals 0 at t equals 1 second and t equals 4.2 seconds. I just kind of estimated there. Actually, I think I did the equation of the line and actually saw what the x-intercept was, but just to save time in this, you could just estimate. But yeah, we could like do points, you know, find the slope of the line, figure out what that actual equation is, and then see what the x-intercept is. Where's the particle moving to the right? Particle will be moving to the right when our velocity is greater than 0. So we're looking at right here, that interval from 0 to 1, and that interval right there. So that's going to be, I'm going to say when v of t is greater than 0, the particle moves to the right. That's my justification, and now let me just give my intervals. 0 to 1, union 4.2 to 6 seconds. All right, on what open intervals or at what times from 0 to 6 is the particle moving at the greatest speed? And then it asks for the greatest velocity. Okay, so speed is absolute value. So you can have either the biggest positive or the biggest negative number. The greatest velocity is going to have to be positive. That you want to have a positive number for. Okay, so the speed is going to be at, let's see, I did that in red. Speed looks like it's at 3 seconds, because -6 is the largest either positive or negative number if we're talking absolute value. So I'm going to say the greatest speed is at t equals 3 seconds. At this time, the speed equals 6 feet per second. Notice I didn't put a negative in there because speed is an absolute value. All right, and then the greatest velocity is going to be from 5 to 6 seconds. And right there, at time equals 0, and from 5 to 6, it's at 4. So I'm going to say the velocity greatest velocity at t equals 0 seconds and 5 to 6 seconds. And the velocity at this time is 4 feet per second. All right, on what open intervals or what times from t to 6 is the particle speed increasing? So we want either both velocity and acceleration to be both positive or both negative. When's it decreasing? We want to have like positive velocity, negative acceleration, or negative velocity, positive acceleration. Okay, so I'm looking at, let's do brown. I haven't used that yet. The speed being increasing, that's going to be increasing from 1 to 3. Because our velocity is negative and also our acceleration is negative because we got that negative slope there. So that's going to be speed increasing 1 to 3. Oh, you know what? Also, we need a positive, so we can look like right here. We got positive velocity, positive acceleration. 4.2, 5 seconds. So the reason being v of t and v prime of t have the same signs. Okay, now we're looking for places where they have different signs. So right here from 0 to 1, our velocity is positive, but we got a negative slope, so our acceleration is negative. And then same thing right there, from 3 to 4.2 seconds. So it's decreasing from 0 to 1, union 3 to 4.2 seconds. v of t and v prime of t have different signs. What's the particle's acceleration at t equals 4.8 seconds? All right, so we're looking for the slope of velocity as acceleration. So we're going to find the slope at 4.8 seconds. All right, so we can use these 2 points right here. This is a nice straight line. So I'm using the point 3, -6, and what's that, 5, 4? All right, so here's our points. I'm trying to move them. Oh, there we go. Now they're sideways. Okay, there we go. Super tiny, but at least we have them there. Okay, so v prime at 4.8 is going to be 4 minus -6 over, that's just your typical slope formula, y2 minus y1 over x2 minus x1, and that's going to give us 5 feet per second squared. Make sure you have your units there correct. And explain what this number means in terms of the particle's velocity. So if our acceleration is positive, our velocity is increasing at 5 feet per second squared at a rate of. All right, on what open intervals or at what times from 0 to 6 is the acceleration of the particle greatest? So we're looking for the most positive or the steepest slope. All right, so that's going to be, let's look back at our graph. 3 to 5 turns out to be the steepest slope there. You can kind of do that. Well, it's the only positive one that we have there, but so that's 3 to 5. This next one, what's the particle's displacement during 2 seconds and justify? The displacement is 0 feet, but we're going to do this more when we talk about integrals later in the year. So don't worry about this question. So we'll do this later in the year. All right, last page, quick fill in the blanks. If velocity is negative and acceleration is positive, then speed is decreasing. If velocity is positive, speed is decreasing, then acceleration is negative. If velocity is positive and decreasing, then speed is decreasing. If speed is increasing, acceleration is negative, then the velocity is negative. Again, hopefully you've paused and tried to fill these in on your own and then checked your answers. Probably should have said that before I started writing these in. And particle moving to the left, speed decreasing, the acceleration is positive. All right, last question, practice. So putting everything together, particle moves along the x-axis so that at time t is greater than 0 hours. Its position's given by, we got a position function right there. All right, at t equals 0 is the particle moving to the left or the right. So before I start this, you know what I'm going to do is just find my velocity, which is my first derivative. 3t squared minus 6t minus 9, because I know I'm going to need them in here. Here's my acceleration, x double prime, 6t minus 6. All right, particle moving to the left or the right. So we are looking for the velocity at time t equals 0. So I'm going to do x prime of t would be my velocity. And I'm going to sub that in. 6 times 0 minus 9. So remember, I'll label this is velocity, right? And that's acceleration. All right, that's going to be negative 9. So that means the particle is moving to the left. To the left, to the left. Because x prime at 0 was negative, is less than 0. All right, at what times, no, orange isn't good. What times does the particle change directions? So we're going to make a sign chart with our first derivative to see where our velocity is going to equal 0 and if we change directions or not. So we're going to factor 3 t squared minus 2t minus 3, so that's going to be 3, t minus 3, t plus 1, t equals 3, t equals negative 1. All right, sign chart, I got negative 1, I got 3, my signs would be plus minus plus, and then let's only look at our positive time, right? So we're really going to just focus on when we're greater than 0, so we're just going to kind of look at this part of the graph. So we're going to change directions at 3 seconds. So particle changes direction. At t equals 3 seconds because x prime of t changes signs. All right, at t equals 1/2 is the velocity of the particle increasing or decreasing? Explain your answer. Okay, so we're going to look at if the velocity is increasing or decreasing, we have to look at acceleration. So we're going to look at our second derivative there at 1/2, and remember we took our second derivative up top there, so it's going to be 6 times 1/2 minus 6, that's negative 3, it's less than 0. So we got a negative number there. The velocity is decreasing because x prime of t is negative. Okay, at t equals 1/2, is the speed of the particle increasing or decreasing? Okay, so looking for the speed of the particle, we need to see what the velocity is doing, if it's positive or negative, and what the acceleration is doing. We already figured out what the acceleration is doing. It's negative in part C. So I just need the velocity, x prime of t, x prime at 1/2, right? So 3 times 1/2 squared minus 6 times 1/2 minus 9. And that is going to be some sort of negative number. I didn't even finish it when I did it on my notes. Minus 3, minus 9. I just knew it was going to be negative. So like in a problem like this, if you don't feel like working with fractions, you can just say, all right, I know that's negative, less than 0. X double prime at 1/2 was also negative, was less than 0, so they were both negative. So I'm going to say x prime of t and x double prime of t are both negative at t equals 1/2 of a second. So the speed is increasing. They have the same sign. All right, find all values of t which the particle is moving to the left. So we just want to look back at that sign chart that we made in part B. And we're looking at where it's negative. So that was right over here from 0 to 3 seconds. So we're looking at that sign chart. When x prime of t is less than 0, the particle is moving to the left. And that is from 0 to 3 hours. Oh, I messed up this should be hours right here instead of seconds. And this should be hours. Didn't realize that we were doing hours instead of seconds. Always read. Always read your directions. All right, last one. If you did this all in one shot, good for you. This is a long video. What's the particle's acceleration at t equals 1/3? Explain with units the meaning of your answer in terms of the particle's velocity. All right, so we're looking at our second derivative here at 1/3 of an hour. Now I know, now that we got to the last part of the problem. So 6 times a third minus 6, that's just going to be -4. And we're miles per hour squared for acceleration. So what this means, we have a negative acceleration, so that means the velocity is decreasing at a rate of 4 miles per hour squared. So I said decreasing, so I didn't need to put in a negative there because that, you can automatically assume that. All right, so that's particle motion in a nutshell.